You can see that I've been a little fast and loose when I'm talking about these examples. In other words, when I was talking about the logarithm base 1024 and the logarithm base 1000, I was more or less using them interchangeably. And just like here, I'm saying it's off by a factor of 3. It's actually off by a factor of 3.3 something. In fact, we'll use log base 2 and log base 10 more or less interchangeably because they're just off by a factor of 3. This kind of approximation is common in computer science, and it's actually necessary because we're typically trying to understand things big picture rather than getting too buried in all the details. One form of approximation is used in our textbook using a tilde notation. And if we have two functions, we can say that they're related by tilde if they're more or less the same. And there's a formal definition in the textbook, but the intuition you should have here is that they more or less fit the same curve. So if you've ever done curve fitting in statistics, you find that you have some data and you try and match a curve. So if two functions more or less match the same curve, then we'll say that they are approximately the same. This level of approximation using tilde is sensitive to constant factors, but often we don't care about constant factors. In order to elide them, we use a notation called big O, or order of growth, or time complexity. When we say that a function f is big O of g, what we're saying is that they're approximately the same using this kind of tilde approximation, but they may be off by a constant factor. So ignoring the constant factor, a, then these two functions are approximately on the same curve. This concept will become much clearer when we start to look at some examples, which we'll do in the next little lecture. Fortunately for us, most of the algorithms that we care about fall into a few categories in terms of their order of growth. If you know these 8 categories, you'll be pretty much set. In this table, I'm going to name the category, I'm going to indicate what the mathematical function is, and I'm just going to try and give you some intuitions about what it means. And down here, I've taken a plot from this paper showing these various functions. When looking at this chart, you should think of the x-axis, the horizontal axis, as corresponding to sort of the size of your input problem. And think about the y-axis, the vertical axis, as being how much time your program is going to take to run. This is what we mean by time complexity. It's how the time required by the program to execute varies with respect to the input size. So if the time of the program doesn't depend on the input size at all, then you have what's called a constant function, indicated by this straight line. If the time required by the function varies with respect to the logarithm, you end up with this purple dashed line here, which is the logarithm. If the time of the algorithm corresponds to the length of the input, as it has for many of the functions we've seen so far, such as finding the max in a list, in that case, we say that the function's running time is linear, or order n. One way to think about linear time is that we're doing a constant amount of work for each element of the input. If we do a logarithmic amount of work for each element of the input, then we end up with what is called linearithmic time, or n log n. If we do a linear amount of work for each input item, then we're going to end up with quadratic time. I've also graphed the exponential 2 to the n and the factorial function in factorial. It's not immediate how to interpret exponentials and factorials in terms of loops, so it's perhaps better to think them in terms of things you will learn in discrete math. So the number of combinations of n items is 2 to the n. That's how many different ways you can select a set of n things. The number of permutations of a set of n items is n factorial. That's not just how you choose them, but also what order you put them in. Understanding exponentials and factorials is important, but fortunately for us, efficient algorithms don't have these complexities. In fact, as we'll see in a second, efficient algorithms aren't even going to be quadratic. Even quadratic algorithms have some serious performance problem as data scales. Most practical algorithms are going to be in one of these four categories: constant, logarithmic, linear, linearitmic, and that's very clear when you look at the graph. Why? You can see that, well, constant and logarithmic are awesome. They grow super slow. And linear and linearitmic aren't that different from each other. If you think about it, we can't often get constant algorithms if we have a data-dependent problem. So for example, the max function over a list, there's no way to compute it in constant time. I can't just guess what the max is. I need to actually look at the data. Therefore, it's going to take me a linear amount of time to go through that data. For each element, I do a constant amount of work, but the total time is linear. So linear work is often unavoidable. And linearitmic isn't that far off, and often it's the best we can do.